What if you could hold a ghost in your hand? An object that could just pass straight through solid walls. It sounds like total science fiction, right? Well, today we're going to talk about how a team of physicists actually made that happen and how that one wild discovery is now powering a whole technological revolution. Look, in our everyday world, the rules are pretty straightforward. You throw a ball at a wall, it bounces back, every single time. But down in the quantum world, oh, the rules get bizarre. A tiny little particle can do the impossible. It can just pass straight through that same wall, as if it's not even there. This spooky action is called quantum tunneling. So here's the big question. What if you could teach that quantum trick to something big, something you could actually see? Could you get a whole system, a whole team of particles to act like a ghost and tunnel through a barrier it has no business crossing? Well, a team of physicists did exactly that. They pulled off a quantum magic trick, but on a massive scale. And for that, they got themselves a Nobel Prize. So the 2025 Nobel Prize in Physics went to John Clarke, Michel Devoret, and John Martinis. The official reason sounds like a mouthful: for the discovery of macroscopic quantum mechanical tunneling and energy quantization. But don't worry, we're going to break down what all that actually means, and more importantly, how they pulled off this incredible feat. So how in the world do you get billions and billions of particles to all act like one single quantum thing? Well, the first step is to get them to march in perfect sync, like a perfectly disciplined quantum army. Okay, so picture the electrons in a normal copper wire. It's just chaos. They're like a messy, rowdy crowd all bumping into each other, each one doing its own thing. In that kind of mess, any of these subtle quantum effects are just totally drowned out by the noise. But in a superconductor, something absolutely amazing happens. You cool it way, way down to extreme temperatures, and that chaotic crowd, it transforms. It becomes a perfectly synchronized army. The electrons pair up, and they all move in absolute unison, flowing with zero resistance. It's wild. The secret sauce here is something called Cooper pairs. The electrons literally pair up, and in doing so, they lose their individuality. They start acting as one single collective quantum system. It's like they all share one identity, moving and behaving as if they're one single giant particle. So, with their quantum army assembled, Clarke, Devoret, and Martinez set up an experiment to see if this huge system could pull off the ultimate quantum trick, a great escape right through an energy barrier. At its heart, their experiment was a simple electrical circuit. Think of it like a lever that's stuck in the off position. There's a barrier in the way, and it just doesn't have enough energy to get over it. So logically, it should stay off forever. But then the impossible happened. The entire system of Cooper pairs just tunneled straight through the barrier, and bam, a voltage suddenly appeared out of nowhere. The lever flipped to on without ever going through the space in between. And get this wasn't just a few particles doing this. We are talking about billions of these Cooper pairs, all tunneling at the exact same moment, all behaving as one single unified quantum object. This was it, the first time anyone had ever seen macroscopic quantum tunneling. But, just seeing this ghost-like tunneling, that wasn't quite enough. To really have a quantum object they could control, they had to prove it followed another really bizarre quantum rule. And this one is the absolute key to building a quantum computer. So they started zapping the system with energy, using microwaves. And what happened was fascinating. If they used low-energy microwaves, nothing. High-energy microwaves, still nothing. But when they hit it with microwaves of one very specific, very precise energy, the system absorbed it and jumped to a higher energy state. It was picky. It would only accept energy in these perfect little packets, or quanta, behaving exactly like a real atom does. And in proving this, they realized they had created something completely new. They had built a controllable, macroscopic artificial atom right there on a chip. A quantum system big enough that you could actually connect wires to it and control it directly. So, a giant circuit that acts like an atom. That's weird, it's wonderful, but why does it really matter? Well, because this experiment from back in the 80s wasn't just some weird curiosity. It laid the direct groundwork for the quantum computers that we're all trying to build today. The theorist Anthony Leggett even compared it to Schrödinger's famous cat. The thought experiment about the cat that's somehow both alive and dead at the same time? The whole point of that was to show how absurd it would be if quantum rules applied to big things. Well, this experiment showed, for the first time, that a system of billions of particles could exist in one of these strange quantum states. It brought that absurdity one giant step closer to reality. The legacy of this artificial atom is just immense. It gave physicists a brand new playground to test the very foundations of reality. But the really big one, it gave us the building block for quantum computers. Remember those specific energy levels it liked? They're perfect for encoding information. You can say the lowest energy state is a 0, and the next level up is a 1. And that is the fundamental principle behind the superconducting quantum bits, or qubits, that power the most advanced quantum computers in the world right now. By proving that the quantum world isn't just trapped in the realm of the ultra-small, these laureates kicked open the door to a whole new era of technology. And that leaves us with one final fascinating question. Now that we can actually build and control these large-scale quantum objects, what are these artificial atoms going to teach us next about our universe?